Hi everyone and welcome to 11.3 Ohm's Law Notes. So please copy these notes down. In case you're having trouble keeping up, please make note of the fact that it is posted under Content, under Unit 1, Electricity, Chapter 11, Current Electricity, and it'll be linked under March 28-29 notes. If you just scroll down, I'll have all of the notes available for today, okay, and also tomorrow. Okay, so let's get started. So we're going to be using a different analogy in order to understand Ohm's law, which analyzes the relationship between the three characteristics of current electricity. Okay, so what we have here is a hurdler. So a hurdler is someone that runs and jumps over like these fence-like post things, okay? And so we're going to draw from this analogy to understand a little bit better, okay? So first of all, in this analogy, for example, we have the athlete, okay? And so the athlete is like an electron, okay? So what's passing through the current or passing through the circuit, the athlete is like the electron. The path on which the athlete travels or runs is kind of like the wires or the conductor. And the food that we eat before racing, for example, that gives us the energy and like the push, let's just say, in order to run, okay? So what we're doing is we're converting that energy into like potential energy, and that's like voltage, that's energy from the battery, okay? Just imagine it would be a lot easier to run on flat ground, but over here what we have are hurdles. And hurdles are like resistors, okay? So it provides some resistance because it slows down, the electrons or slows down the athletes. You could imagine that if there were many hurdles, this would slow down the runner more and more and more, okay? The amount of energy before the hurdle versus after the hurdle, we might consider that to be called the potential difference or voltage. So when we think of potential energy, potential difference, or voltage, we can kind of use them interchangeably in grade 9. But when you get into grade 11 physics, grade 12 physics, that's where you're going to start understanding the nuances and the differences between those three. Okay. If we have the number of laps per minute, this would be like the current. Gosh, this is like in the way. This would be like the current. And then if we had a coach who's kind of like timing on the sidelines, that would be like the ammeter, which is a meter that reads how many electrons goes through. So an ammeter is the measuring device that measures current. Okay, so that's the analogy, okay? Let's just keep going with this a little bit more, okay? So for example, what happens when you increase the hurdles or increase the resistance? Then in the analogy, the athlete doesn't get through as many laps. So what happens to current in this case if we increase the resistance? Well, the current will decrease because we're increasing the resistance. Then the current, or how fast the athlete goes through, the runner goes through, will actually decrease. Okay, this is this is an imperfect analogy, okay? But let's just say, for example, you eat more before the race. This means you're increasing the voltage. You increase the energy. That means you might be able to go faster. So what happens to the current then in this case? If you are able to go faster, okay, then that means that the current increases. Okay, so when we're talking about Ohm's law, we're just understanding in terms of like the concepts, how one thing affects another, okay? And these would be like questions on what we've just covered right over here, like increasing the resistance and what happens to the current, the fact that it decreases. These are questions that might be, for example, multiple choice questions on our quiz. Okay, so please take some time just to review this when you get home and really understand the concept. Okay, here is that same analogy that we showed just before, okay? But over here we've got ohms, we've got volts, and we've got amps, okay? And so we're gonna make associations. So ohms is actually the measure of resistance it's like the unit for resistance. So resistance is the quantity. We use the symbol R, and this is the symbol for ohms. So this is ohms, and this is the symbol. Okay, just write that down so that you have it. Although I do give another handout as well for this. Okay, that outlines everything. Okay, next up at B we have the amps. Okay, so these are like the electrons passing through the pipe. Okay, and at B it's like the current. It's the electrons passing through the pipe or the wire. Current is the quantity. The symbol that we use is I, and then the unit is called amps or amperes, and the symbol for amps is A. Okay, so it's very confusing because current is C, but then it's I, and then it's A. So for this one in particular, it's a little bit confusing. Please make sure you make proper associations with that, okay? And the reason why they use the letter I is actually because originally they called this electrical intensity, okay? I for intensity, but they've since changed it to current, okay? Lastly, at C, we've got the voltage or volts, okay? Voltage in V is pretty simple. Again, that is the electrical pressure that's pushing the electrons through the circuit. Okay, so let's just go through some of these items here. So, for example, what happens if at A, this person tightens the rope? Well, if this person it's getting narrowed right over here, then B goes through slower. Okay, so if this is going through slower, what happens to current electricity? Well, then current decreases. Okay, so once again, these are kind of like, we're using this analogy to understand, but we are kind of preparing ourselves for questions that might be on a test or a quiz that test our understanding of how something such as resistance increasing will affect the current in a circuit. Okay, what happens if A loosens the rope? That means that this person or the electrons will be very free to pass through, so they'll be passing through faster. And when current or this item is passing through really fast, this means that current increases. Okay, what happens if, for example, at C, this person pushes less? That means that voltage decreases. Well, if voltage decreases, that means they're pushing less. That means that over here, this person, if they're getting pushed less, it means it's slower, and it means that current decreases. And then, of course, the opposite is also true. If C is pushing more, there's a more electrical pressure, then the current increases. Okay, we're going to see a little bit more about this. Please make sure you copy down these notes, and then we're going to turn the page. Okay, so over here, let's just summarize. Okay, so V is equal to I times R. This is the this is the formula for Ohm's law. So V is voltage, which is equal to I, which is current, times the resistance. Okay, so what we're going to do here is we're just going to examine what happens when we keep certain things constant, and if we increase one, what happens to the other item. Okay, so let's just say, for example, within Ohm's law, we know that this is true. Okay, so voltage is equal to current times resistance. Let's just say we are keeping the resistance constant. Okay, we're keeping the resistance constant. That means that over here, the tightness in this little tube right over here, the amount of resistance that's being provided or being supplied in the wire, that is being kept the same. Okay, so what happens when, the question is, what happens if, for example, the voltage increases? Well, if I'm keeping the resistance constant and the voltage increases, that means the electrical pressure is increasing. What does it say about current? Well, it means that current is also increasing as well. Okay, so let's just think about this. The resistance is the same. If I'm going to increase the electrical pressure that's pushing, it means that what will happen in my circuit is that the flow rate, the number of electrons passing by a certain point, will also increase, okay? And so then what we say is that voltage is directly proportional to current. So these two things, when one thing goes up, the other thing also goes up, okay? Now what we're going to do is we're going to keep, again, the resistance constant, okay? If the voltage decreases, that means the electrical pressure is decreasing. That means that the current must also be decreasing, okay? We could also say it the other way. If we're keeping the resistance in a wire at a certain resistance, if, for example, the current is decreasing, we can conclude that the voltage must also be decreasing as well. Okay, so they are directly proportional to current, voltage and current. Okay? Okay, now we're going to shift gears and now we're going to say, okay, we're going to keep the current, that means the rate at which electrons flow by, we're going to keep that constant. Okay? Then what happens to these other items? Okay, so for example, if the current is the same and I increase the voltage, okay, so the amount of electrons flowing through, it's happening, let's just say, at a certain pace, okay, 1, 2, 3, 4, okay? If I'm increasing the push that's behind each electron, what must be happening to the resistance in order for the current to remain the same? Okay, this is counterintuitive. It's a little bit confusing. So if the flow rate is the same, but I'm increasing the push, well, that must mean that if this is constant, that must mean that the resistance must be increasing. Okay, as well. Okay? Next up, if again, I'm keeping the flow rate exactly the same, and for example, let's just say the resistance is decreasing, so it's actually, there's less resistance, but somehow my current is remaining the same, well, I can conclude then that what's actually happening is that the voltage is also decreasing as well. Okay, so I don't know if there was these changes made already on my newest handout, but voltage is also directly proportional to, so I don't want you to write down current, it should be resistance. Okay, I think I changed it, but I'm not sure. Okay, lastly, if I keep the voltage constant, that means that the electrical push that's behind every single electron is remaining the same. If I have increased the current, that means the flow rate is actually increased, but somehow the push behind my current is remaining the same. The interesting thing is that that means that in order for the current to increase while having the voltage constant, it must mean that there is an inverse or indirect relationship. It must mean that the resistance is actually lowered. Okay, so if I'm keeping the electrical push the same, but somehow my current is increasing, okay, and my current is increasing, that means my flow rate, even though I haven't increased the push, that means that something must be happening to the resistance. It must be lowering in order for the current to be actually increasing. Okay, again, we're keeping the push the same, and if we, for example, lower the flow rate, if we're lowering the flow rate somehow, that means that the resistance must be increasing. Okay, so what we say is that current is indirectly proportional to resistance. Okay, these are conceptually quite challenging. Okay, and that's okay. So take a moment, review that, okay, and try to figure that out. Okay, I'm just going to reveal these really quickly because these are Ohm's law, the three different formulas, okay? But I'm going to get more into that in the next lesson.